So light exhibits these wave-like properties. Light also exhibits wave-like behaviors. Light can reflect, refract, diffract, and interfere. So let me review these with you. Remember, reflection is the idea that waves can bounce off of other objects. We all know this, right? If light could not bounce off of things that none of us could see, you wouldn't be able to see your beautiful glowing face in the mirror. Light can reflect, right? An interesting thing about the reflection of light is this rule right here. We say that the angle of incidence equals the angle of reflection. So incidence means incoming. So imagine that you have a mirror, and imagine that there's an imaginary line going straight up from that mirror. The angle that your incoming light makes with that imaginary line has to equal the angle that the reflected light makes with that imaginary line. The angle here, the angle of the incoming light, has got to equal the angle of the outgoing light. Angle of incidence equals angle of reflection. Just an interesting fact about reflected light. Light can also be refracted. Remember, refraction refers to the fact that that waves can bend when they travel from one substance to the next. This is a little bit complicated because I know you're thinking, wait a second, Mr. Thurman, light does not travel through matter, so how can different types of matter affect it? How can light be bent as it travels through different types of matter? Well, light does not really travel through matter, that's true, it does not have to do that, but it can be bounced around by matter. So we can think about it in the same way that when light goes from one substance to another, it's still going to get affected, it gets bent. That's refraction. When we analyzed refraction last time, I gave you the example of a straw in a cup of water. The straw looks bent. This is why. Light is a wave and light can refract. You can see here that this fish to this spear hunter seems to be right here, but it's actually right here because the light has been refracted. This is what prisms do. This is what water droplets in the atmosphere do to cause rainbows. They diffract light. It turns out that white light that we get from the sun, we're going to talk about this later, is actually composed of many different types of light, many different colors of light. And they all get bent, they all get refracted differently. So if white light comes in, and then every color trapped in that white light gets bent a little bit differently, then the white light literally gets shattered or split into different colors, and we get a rainbow effect. That's what's happening right here. That's what happens in the atmosphere with the rainbow. By water droplets, that's what's happening with this glass prism. It is refracting the light. Light can reflect, light can refract, light can also diffract. Diffraction is just the ability of a wave to bend around obstacles. This diagram is kind of confusing, don't worry about it, but all I'm showing you is that if there's a source of light, light travels out as a wave. There's an obstacle or a slit, light can travel through that little slit and bend around it. That's what we see happening here. This is light that's passing through what we call a double slit, and you can see that the light is bending back around that slit. This is what a red laser shining through a single slit just like this would look like. You're not going to get a single focused dot because the light bends back around the slit opening and ends up spreading out. This is the pattern you're going to get if light is shown through a double slit like this. Why is this happening? Well, it turns out that light can also interfere. Do you remember interference? Interference is when two different waves can add together to make a bigger wave, or they can cancel each other out to make no wave at all. Well, guess what? Light can do that because light is a wave. So imagine we have light shining through two slits. Both the slits diffract the light, and then eventually the two wave patterns are going to meet up and affect each other. Wherever peak meets peak, we're going to get bright light. Wherever peak meets trough, we're going to get no light that's been canceled out. And so we're going to get what is known as an interference pattern, which you can see right here. We're going to get a bright band, a dark spot, a bright band, a dark spot, a bright band, a dark spot, so on and so forth. Here's another picture of that. Here you can see light coming in, traveling through double slits, and this is the interference pattern. You get alternating bright and dark bands because, once again, the light is interfering with itself. This is actually how it was determined first of all, that light is a wave. This dude named Thomas Young literally performed this double slit experiment. Um, Two tiny slits very close to each other, incoming light. He saw this interference pattern, and he knew that, wait a second, the only thing capable of making that is a wave, so therefore light must be a wave. Thomas Young, this was in the 1700s, I believe. There's a really cool video where a guy replicates this experiment. It's going to be posted on the website, so you could watch that. But Thomas Young is the first one to conclude that light's a wave because it's capable of interfering. So light has wave-like properties. It can reflect, refract, diffract, and interfere. So let's keep going through our journey of the wild world of light. It turns out that because light has frequency and wavelength and it carries energy, light can actually come in many different types, which we humans have classified based on the frequency, wavelength, and energy of the light wave. And we refer to those types as occupying the electromagnetic spectrum. The electromagnetic spectrum describes these types of light that we humans have categorized. This is a picture of what the electromagnetic spectrum is trying to communicate. This is a little picture of what a light wave would be. So on this chart, this is just a chart, just a model to help you understand the different types of light waves. As you go from left to right, we have increasing wavelength. So the wavelength gets larger from left to right. That means the frequency gets smaller from left to right. Remember, frequency and wavelength have an inverse relationship. So over here on the far right, we get the largest wavelength, but the lowest frequency. And remember, frequency and energy are directly proportional. So the higher the frequency, moving to the left, the higher the energy. And once again, these are just types of light that we classify. Of course, everyone's favorite type of light, the light that your eyes have evolved to interact with and receive information about, is visible light. It's an incredibly narrow little sliver of the whole spectrum. But here's visible light. You need to know that visible light has a wavelength range of about 400 to 750 nanometers. If that seems tiny to you, then just imagine all these other types of light, whose wavelength is much smaller. The light that has the shortest wavelength, the highest frequency, and therefore carries the most energy is gamma rays. Gamma rays are a type of high energy light that's given off in certain atomic radioactive processes. There are some really big astronomical objects like certain types of stars that also give off gamma rays. And gamma rays are incredibly dangerous and harmful to living things because the light is short enough, the wavelength is short enough for the gamma ray to slip in to your cell, into the nucleus of your cell, and do some damage to your DNA. And guess what? If your DNA gets damaged, and if it causes random mutations, that's going to be bad news bears for you because the DNA is the storehouse of your genetic information. It makes you you. So gamma radiation can cause cancer and, in some cases, instant death. So no, the Hulk is not scientifically accurate. And gamma rays carry the most energy, right? So you do not want to get hit by a gamma ray. X-rays are next. They have a little bit longer wavelength, a little bit shorter frequency, a little bit lesser frequency, less energy. And X-rays have just the right wavelength to pass through soft tissue, but get absorbed by solid hard tissue in the human body. This is why X-ray pictures work to help doctors look at your bones and things, because the X-rays slip right through your soft tissue, your skin, your muscle, your fat, things like that, but they get absorbed by your bone, and so they can be used to make pictures of your bones. X-rays can also cause damage to DNA. Ultraviolet light is next, longer in wavelength, shorter in frequency, lesser in energy. You know that the sun emits a lot of ultraviolet light, and it is harmful to skin cells. And then we have visible light, which we've already discussed. Infrared light, by the way, these terms, ultra means higher. So this is a higher frequency than violet light. That's why this part of the spectrum is called ultraviolet, because it lies beyond violet. Infrared, that term infra means below, so these are lower frequencies than red light, infrared. Infrared light is a light associated with carrying heat. Some critters in nature can sense infrared radiation, like snakes, I believe, can sense infrared light. Um, you guys have heard of night vision goggles and heat-seeking technology, things like that. Well, they pick up infrared radiation. Infrared is the type of light that carries heat, that carries thermal energy. Going even shorter now, no, excuse me, going even longer in wavelength are microwaves, lesser in frequency, lesser in energy. Microwaves, you all know and love, as a type of light wave that's generated by that device in your kitchen that artificially heats up your food. Microwaves have just the right wavelength to hit and interact with water molecules and excite them, cause them to jostle around, vibrate, rotate around. And so the way that your microwave in your kitchen works is it blasts your food with microwaves, microwave radiation. And once again, the wavelength is just long enough to interact with water molecules, so all the water molecules in your food product get jostled around, and your food gets hotter. This is why microwaves are not good at distributing heat evenly, because if there's a part of your food that you're heating up where there's lots of water, it's going to get heated up first. If your food is relatively dry, if there's not much water in it, a microwave won't really even work that well to heat up your food. It's got to have water. Microwaves are just the right wavelength to jostle around water molecules. And then longer than that, we get radio waves. Radio waves are the longest waves, the shortest frequency. They have the less energy, the lowest amounts of energy. And you know that radio waves are traveling all around you right now. Somewhere in here, in between microwave and radio wave, somewhere in this part of the spectrum, is the type of light wave that your cell phones interact with. They pick up and they transmit light waves uh, in this spectrum, this part of the spectrum. Same thing with your Wi-Fi, all the stuff that we know and love and need for our modern day lives. It's a type of light wave traveling through the air, bouncing around through the air, which we will talk about. So this is the electromagnetic spectrum. Light is a wave. There are different types of light that we can categorize based on their wavelength, their frequency. Remember, wavelength and frequency are inversely related, and based on their energy. Remember, energy and frequency are directly related. Higher frequency means higher energy. That's the electromagnetic spectrum.